This video is going to cover section 4.2, still part of Unit 4, Trigonometry, Trigonometric Functions, and the unit circle. For this one, I will be using this little foldable. Hopefully you have it. Basically, it has the main circles that we have. So, 40, pi fourths, pi sixths, and pi thirds, and the corresponding ordered pairs that go with them. Okay, so we're going to be using that for some of the examples here. Let's start off with this unit circle. Okay, so the unit circle is super useful when it comes to trig. It's basically a circle on the xy plane that has a radius of 1. That's why it's called the unit circle, 1 for unit. Okay, it's defined by x squared plus y squared equals 1. This is something you learned the last semester. Here is what it kind of looks like with, hardly anything on it. Basically just our 4 main points. So if this right here is our radius, so from the center to the edge, okay, r would be equal to 1, which means that this first point right here would be 1 comma 0 because it's a distance of 1. If you think of a radius from the center going up, well, that point's going to be 0, 1 because again, it's still just 1 unit away from the origin. This way we have -1, 0, and this way 0, -1. So all of these are just 1 unit away from the center. So that's where we get these 4 points from, and they're kind of important, okay? This angle right here, this is going to represent our either degree or radian measure. Basically, if we have this angle and we have a measure that relates to it, so like our arc right here, this point right here is represented by some x, y, or we can also call it some number t, some real number t, so an arbitrary number. Okay, that's what this is representing. This t represents basically the distance this way and up, which is our ordered pair x, y. Okay, so let's go ahead and look at some very basic definitions here. Okay, we have trigonometric functions, where t is just some real number corresponding to that point, x, y, on the unit circles. It can be any number on that circle. If we do have that point, then we have these 6 trigonometric, I guess you could not identities, functions, where sine of the number is equal to the y, cosine is always going to be x, tangent is the y divided by the x. And again, these x's and y's are just the ordered pair that we're going to be looking at. Okay, these ones are kind of special. This stands for cosecant, this is secant, and this is cotangent. Okay, so I'm not going to write them out for you. You can look at your book if you want to see the spelling. But basically, they are just the reciprocal of these 3. So if you notice, this one's equal to y, this one is 1 over y. This one is x, this one is 1 over x. This one is y divided by x, this one is x divided by y. So it's just the flip version of our 3 main trig functions, okay? Take a note that whenever you do have denominators, you don't want those to be equal to 0 because that means they will be undefined there, okay? And if they are equal to 0, then at that point, this trig function would be undefined, okay? Let's go ahead and do some examples right off the bat. Example number 1, this has a whole bunch of parts to it. It says use the trigonometric functions and the unit circle to evaluate the 6 trig functions at each real number. Okay, so we're going to be using our little handy dandy foldable, the second one that I did here, to evaluate some of these. It says when t is equal to pi over 6. What we're looking for are the 6 trig functions. So the 6 trig functions are basically these ones, the ones that you wrote on this page, those ones right there. Okay, so we're going to start with sine. So sine of pi over 6, okay? This is supposed to be equal to y. Remember that this is equal to the y. So what we're going to do is we're going to look at our little foldable here, and I'm going to look for pi 6, which I believe is this one. Yes. So here's pi 6, and I'm looking at this angle right here. These are the ordered pairs that go with it. And I'll show you how to find these later on, not just yet. Okay, there is a real reason why these equal what they are. But we're looking at the y value here. So the y value is 1 over 2. So equals to 1/2. And we're done with that one. That's 1. Cosine of pi over 6 is next. So cosine, again, it's the same little part right here, pi over 6 is the x value. Remember, this one is equal to x. It's going to be this first one, square root of 3 over 2. So square root of 3 divided by 2. And we're done with that one. Tangent of pi over 6. So here's where it starts getting a little bit interesting, because according to what you wrote on the previous page, tangent is y over x. Okay, so I'm going to look at my y and my x, and I have to divide them in that order. So y divided by x. So it's going to be 1/2 divided by square root of 3 over 2. Okay, so here we have to do a little bit of work because we can't just leave it like that. So we're going to do our keep flip change, where this is going to be equal to 1/2. So keep this one. We're going to flip this one. So square root of 3. Let's rewrite that. It's kind of messy there. So 1/2, keeping that one. We're going to flip this one. So 2 over square root of 3. And we're changing that division to multiplication. Well, we can see from here that the 2's are going to just give us a 1. So we're left with 1 over square root of 3. And now this is not allowed. We're not allowed to have roots on the bottom. So what we do is we multiply the top and the bottom by the same root here. And that's going to give us square root of 3 over square root of 3 times square root of 3 is just going to be square root of 9, which is equal to 3. So this is our answer. This right here, a really quick way to do it, this is kind of like the work, but a really quick trick for this is to basically take this number, put it on the top, and then leave the number that's there on the bottom. Okay, so I'm going to go through these kind of quickly. If I need to go over a little bit more on this, just let me know in class, and I can definitely do some more examples with this part right here. Okay, right? It's called rationalizing the denominator, is what it's called. All right, so tangent of pi over 6 is square root of 3 over 3. Okay, so that's the first three. Now we're going to do, because there's 6 of them, right? Remember, there are 6 trig functions. We did the first 3, sine, cosine, tangent. Now we have to do cosecant, secant, and cotangent, which are just the flipped versions of these ones. So all I got to do is flip them. Okay, so let's go ahead and do cosecant next. So cosecant of pi over 6. Remember, this is equal to 1 over y. So basically, it's going to be this number flipped. And we can show the work if you'd like. 1 divided by 1/2 is the same as 1 times 2 over 1, which is equal to 2. Do it like that. So 1 over 2 is the same, if I flip it, is the same as 2. Okay, so there's cosecant. Secant of pi over 6, well, this is the same as 1 over x. Okay, so I'm just going to look at what I had up here for x. It's square root of 3 over 2, so I'm going to have to flip that. So 1, I guess we can just, well, let's go ahead and do it. So 1 divided by square root of 3 over 2, okay? This is the same as 1 times 2 over square root of 3, which gives me 2 over square root of 3. And again, we have that root on the bottom, which we're not allowed to have. So here is the shortcut for this, okay? This is what the shortcut. Whatever's on the top stays on the top. This number, remember, you're actually going to multiply the top and the bottom by it. So we end up with square root of 3 up here. And if you multiply square root of 3 on the bottom again, the roots kind of, I don't want to say cancel, but they kind of neutralize each other out, and it just ends up as a 3. So this is the answer for secant. Okay, and last but not least, cotangent of pi over 6. Okay, well, it's going to be the same as x over y, which is just the flip version of whatever I had up here. So let's just go ahead and do that. We're going to have 3 over square root of 3 because my tangent was this one, right? So if I flip it, all I have to do is flip them. Notice that for these two, I did kind of go through the motions. I said 1 over, then I did it. And it came out to the exact same thing that I said, just flip it. So for this one, I just went ahead and went right into the flipping, okay? Now again, we can't have this, so we're going to rewrite this 3 square root of 3. So this guy comes up. We're left with the 3 on the bottom. These 3's are going to give me a 1, so we're just left with square root of 3 for cotangent. Okay, and those are the 6, I should say answers for our 6 trig functions here, using those points. And where did we get these points? We got them from our pi over 6 little chart here. Okay, so basically these two numbers right here. And again, I will show you how to construct these numbers a little bit later. Okay, I'm going to go ahead and we're going to save these two, B and C, for class, but it's basically the same way. Notice that these are pi fourths. So for this one, you would be using the one that has the pi fourths. So I encourage you to try them by yourselves first and see if we get the same answer in class. Okay, let's move on to our graph of sine and cosine. So we're finally getting to some actual graphing. Because so far the unit circle, there hasn't been too much graphing. It's more like a circle. Here's some points. This one, we are going to use our unit circle to find y equals sine of t. I went ahead and changed it to t just because that's how it has it in your book, but typically you do use y and x. Remember, t is just representing some real number, so we don't confuse it with the x values here. So here's how this is going to work. I go ahead and copy this chart down first, so we're going to do it with a table, okay? And what we're going to do is we're going to evaluate each value of sine at these x values. Okay, so when x is equal to this number here, what is y going to be equal to? Okay, remember that sine is the, oh, I'm sorry, this should be a t, not x. This one should be a t, so there's no confusion. I think that's why we use t. So when t equals these values, we're going to plug it into our function and see what does y come out to. Remember that sine are the y values. Okay, so we are going to use our unit circle for this. Let's go ahead and take that out right here. Okay, so for the first one, at sine of negative pi, okay, notice that all of these ones, and I guess we can use, okay, so we kind of have to use a combination because we don't have negative pi on this one, but we do have it on the other one. We know that negative pi lands in the same spot as pi, because if you go backwards, well, this is still the halfway point. So negative pi is going to be right here in this area. So if I compare that to this right here, my y value is 0. So we're looking at this number right here. My y value is 0. So the very first one right here is going to be 0. And I'm going to plot that up here. So at negative pi, my point is 0. Next is negative 3 pi fourths. Okay, so negative 3 pi fourths, it has a denominator of 4. Okay, so I'm going to look at my pi fourths one. So again, we're going to use a combination just because it's the negative ones. And let's see, I want pi fourths. So that's going to be the middle one. Okay, so I have negative pi fourths, negative pi halves. Negative 3 pi fourths is right here. It's this section right here. Okay, so I'm going to cross-examine that with my chart over here. It was this section right here. And I'm looking at the y, so the y is negative square root of 2 over 2. So that's going to go next, negative square root of 2 over 2, which is some really weird number. If you check it out in the calculator, I think it's like negative 1.7 something. So, or negative 0.7 something. So I want to estimate that one to be about maybe right here. So negative 3 pi 4 and negative square root of 2 over 2 is probably about somewhere there. I'm just kind of estimating this one. Okay, and you can plug it in the calculator and see a more accurate answer. Next one, negative pi halves. Okay, so now we're going to look at negative pi halves and say, where is negative pi halves located? For this one, it doesn't matter which one you look at because they all have pi halves. We want the negative one though, so there is negative pi halves. It's the same for all of them, negative pi halves, and oh, this one doesn't have it, so let's just look at these two. So it's on the bottom. Okay, it's basically on the bottom. So if we look at the bottom here, negative pi halves is this piece right here. My y value is -1. So -1 is my next one. Negative pi halves, -1. So far I have something kind of like this. This should be a little more curved. I'm just not very good at drawing these. Okay, it's probably going to go up like that. So it looks like this so far. Okay, negative pi fourths is next. So again, let's check. Hopefully you can go a little bit faster than me. The pi fourths is the middle one. So there it is. It's going to be this wedge right here. So it's this wedge right here. And I'm looking at the y value again, negative square root of 2 over 2. So it's the same as the other one. So negative square root of 2 over 2. And I put mine about right there. So far it's looking kind of like this. It should be a little kind of more curved, but you know, I'm not very good at drawing most of the time when it comes to graphs. Next one, sine of 0. So that one shouldn't be too hard to find because 0 is right in the beginning, right? 0 is right here. It always starts here. So my y value here is 0. So there it is. And it should look kind of like that so far. So it's kind of like a little mini parabola, right? Moving on. So this one was 0. Pi fourths. Now we can go ahead and look at this one because these are all positive. So pi fourths, let's go a little bit faster. Sine of pi fourths, this one is pi fourths. Okay, this first one is pi fourths. The y value is square root of 2 over 2. You should be noticing a pattern at this point. Square root of 2 over 2. So pi fourths, square root of 2 over 2. Let's see, it's going to be somewhere, I don't know, here-ish. So it's looking up. It's going up again. Okay, sine of pi halves. Okay, sine of pi halves. So now I'm going to go to my pi halves, which is right here. And the y value is 1. So this one's going to be 1. And there is my 1. Okay, so that looks a little bit better than the other side. Sine of 3 pi fourths. Okay, so we might have to count a little bit for this one. Remember, it's 1 pi fourths, 2 pi fourths, 3 pi fourths. So this is 3 pi fourths. Square root of 2 over 2 again for the y. So square root of 2 over 2 for the y, which is going to be kind of like this where this one is also located. So we have something like this. You should kind of see a little curve thing going on. Sine of pi. So pi is right here. The y value is 0. So 0. So my picture is not too great here, but it looks something like this so far. Okay, and then we skipped ahead a little bit because I didn't want to do the entire every single thing just because of the time. But the next one I have is 3 pi halves. So 3 pi halves is at the bottom, and the y value at this point is -1. So this is -1. Okay, and then 2 pi, which is the last one, 2 pi is back right here at the end, which is just going to be 0. So my last two are -1 and 0. So 3 pi halves, -1, 2 pi, 0. So something like this. And you're going to notice that there is a pattern to this one. Yeah, it repeats itself. This little piece right here is going to be the same over here. Yeah, so the reason this repeats is because this is actually what we call a periodic function, where you're going to have the same kind of deal going on over an interval for a certain amount of time. So the period is actually something we're going to be looking at a little more carefully later. But it's, in other words, it's going to repeat between between two numbers. In this case, negative pi through pi. This is the pattern we're going to see. So if I could pick this up and copy paste it, I could. It would land right on top. Over here, the next one would probably go up. On this side, it's going to go up. So the pattern is concave up, concave down, concave up, concave down. And this happens every 2 pi. So pi, pi, every 2 pi. So that's kind of important, yeah? The period of this, and this is some more stuff you got to copy, is going to be equal to 2 pi. In other words, every time you do a revolution on the unit circle, okay, the one that we're looking at, this graph is going to have that little roller coaster looking design, okay? Now, let's answer the other parts. The domain of this function, well, it's going to go on forever, right? So it's going to be all real numbers. The range of the function, however, notice that it does not go past this number or the top number over the 1. So the range for this function is actually between -1 and 1. And that's all there is to that, okay? A note here at the bottom, it says, since this is directly related to the unit circle and sine of t is equal to y, we can get the range directly from the unit circle as well. So that means that if I look at my unit circle, okay, well, I know that the y values are between -1 and 1. So that is how it's directly related to that. So the next graph we were going to look at, and again, I think I might just do this one in class, but you could go ahead. Well, I guess we can do it real quickly. It won't take too long. Is y equals cosine. So cosine is the other one of the three, one of the other trig functions that we're going to see a lot of. It's good to know that when we're dealing with cosine, we are dealing with the x values. And I didn't write that on the other side. This one, y, was the sine values, okay, just like it showed on the very first page. So I went ahead and entered these values, and it's done the same way. You just look at the little circle, you see what the x value is, and there you go. But if you have any questions, of course, let me know. Notice that this one is very pattern-like. 1, 0, -1, 0, 1, 0, -1, 0, 1. So it's also kind of doing this periodic behavior. So let's notice that the one from before started at, we kind of had this in the center, it has this odd symmetry, right? This one, cosine, is actually more like an even function. It's symmetric if I were to take my paper and fold it, this way over the y-axis, and it starts at 1. So that's kind of important also, but it does have a period of 2 pi, just like the one before, because you can see that, for instance, if we start here at pi, it's going to go up, down, all the way to here, and then it repeats. So between these two numbers, you have the repeated pattern, okay? So just like the one before, the period for this one is going to be 2 pi. The domain of this is also going to be all real numbers because, well, it's going to go on forever, left and right. The range, this one also is between these two numbers, okay, -1 and 1. So -1, comma 1, and it is with brackets, just like the one before. If we keep going, it is the same as adding 2 pi to the unit circle. So for both sine and cosine, this is kind of a summary for both of them, okay? So if we were to keep going for both of these functions, this right here is true. In other words, all I have to do is add 2 pi to each one times n being any numbers, so 2 pi times 1, 2 pi times 2, 2 pi times 3, etc. And it would give me the exact same function, because even if I add another if I take this and I add it another time over here, if I were to translate this over, think of it like a transformation, okay? Well, since the pattern repeats over here, it's going to land right on itself. So it's the exact same function, which tells us that as long as I don't change anything else, if I'm just changing something inside the parentheses, like a plus or a minus 2 pi times some integer number, it's going to be the exact same thing, okay? And that's what this says right here, for any integer n, and t is any real number, okay? These are examples of periodic functions because they repeat for a period of spaces, I should say, okay? I think we're almost done. Last but not least, here we have the official definition for a periodic function. It's a function f that is periodic when there exists a positive real number c, such that t plus that number c is the same thing. Okay, so again, like I mentioned, if I were to pick it up and move it over, it doesn't matter because it repeats, so it's going to land right on top of itself. For all t in the domain of f, the smallest number c for which f is periodic is the period of f. So it means the same thing. Okay. Some more things here. You kind of heard me say something about even and odd. Remember that even means that it's reflection over the y-axis, so y-axis symmetry, where my positive values of x or t or whatever this is are going to be the same as the negative sides when it comes to the y. So this side's going to match this side. Odd symmetry is kind of like a diagonal symmetry. It's a rotation of 180 degrees that if you turn it will land on itself, or you can also do that double flip, 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 and it should land on itself. Some of the properties we have with these trig functions, even functions, are cosine and secant. Remember that secant is the same as 1 over cosine of t. So this is just the reciprocal. I guess I could put negative t because that one's negative. But this one's just the reciprocal of this one. It's just the flip version. So if you were to flip the function, it's still going to have that even symmetry. Okay, so these are even. The odd ones are basically everything else. Sine, cosecant, tangent, and cotangent. All of these, if you graph them, if you graph this one and you graph this one, they're going to have that kind of like that diagonal symmetry. Okay, and they're a little bit harder to see because, well, I know that they just go straight across, but with all the flipping, it does come out to the same, and this will be true. Okay, so with that in mind, let's answer just a few more questions, and then we're done with this section here. Example number 2, use the period of either the sine or cosine function to evaluate these two. This one, I'm not going to use symmetry so much. I'm going to use my little circle. And I'm going to remind myself, I guess I can use, let's see, we're using 9 pi halves. So for this one, I can use whichever one actually, because 9 pi halves is not too hard to visualize. So when we're thinking halves, okay, you are thinking, this is pi halves. This is, okay, so this is 1 pi half, 2 pi halves. Remember, 2 pi halves is the same, or do I have it on the other one? Oh, that's okay. 2 pi halves is the same as pi. So 1 pi half, 2 pi half, 3 pi halves, 4 pi halves, 5 pi halves, 6 pi halves, 7 pi halves, 8 pi halves, and 9 pi halves. So we can use our unit circle that way. 9 pi halves lands right here, and they're looking for cosine. So the x value here is 0. So the answer for the first one is just going to be 0. Because of the period, because every 2 pi thirds, so now we're looking at the pi thirds one. So I'm going to use, I'll use the other one this time just so you can see how we can use both of them. So pi thirds is this circle here, and I'm looking at -7. So remember that the negative angles, those go backwards, okay? So you can already see that I do have a few written down. I have negative pi thirds, -2 pi thirds, -3 pi thirds would be this one, -4, -5, -6, -7. So -7 lands right here. And again, all I'm doing is counting -1, 2, 3, 4, 5, 6, 7. So it's going to land on this piece right here. So if I cross-examine this piece with my other one right here, with this one, okay, I'm looking at, what am I looking for? Sine. I'm looking for the y value. So my y value here is negative square root of 3 over 2. So negative square root of 3 over 2. And if you don't have these foldables, you might want to write them down, guys. They come in handy a lot, unless you want to do, all the work for them. And the work for each one is lengthy. I haven't shown you how to do that quite yet. So I recommend you write them down. Last but not least, and I said that like 2 minutes ago, it says to evaluate cosine of t, given that cosine of negative t equals 0.3. This one's a little bit confusing if you're not sure, because we haven't seen 0.3. 0.3 is not exactly a radian or a degree, or we don't know what that means. So we're going to go back to our even and odd stuff up here and say, do I have anything with a cosine negative t? Well, I do have this one, and it tells me that since cosine is even, if I have this value, then I have this value, meaning they are the same. So if cosine of negative t is 0.3, then cosine of t is also 0.3 because cosine of t equals cosine of negative t since they are even functions. Okay, and I believe that that is it for this video. If you have any questions, as always, let me know.